So this slideshow is something that I've developed to do public outreach myself and to have my colleagues and students who want to do public outreach can customize this slideshow and do it at their universities. And I try to answer the question, what's the big deal from the physical standpoint with climate change, and why are scientists so worried about a small temperature increase, a degree, 2 degrees. And I would like to think that I'm using reputable sources, which I have cited and provided to you. If you have any questions about the content, feel free to email me. My email and web address are in the handout. So the sources that I'm drawing from, you may have seen them before. One is the middle one here, the IPCC. This is the group that got the Nobel Prize for their work on climate change. And they have a brief, like 20-page summary of the science of climate change, which I'm using for some of my slides. There's also a presentation that I've customized from the Hadley Center in Britain. And then U of I alum Jim Hansen, who's currently at NASA, I've customized some of his materials as well. And if you would like to give this presentation yourself, let me know, and I can provide it and the sources to you as just a zip kind of thing. So about me, I've already said the first 2 bullet points. I'm assistant professor of chemical biochemical engineering at the University of Iowa. I'm an informed amateur, so I have to be informed to do my research, which is in the carbon cycle. So I study fluxes of carbon in the environment, and I also study pollution aerosols, and those pollution aerosols affect the amount of energy that can get to or from the Earth. And so that's how I got into this. I teach thermodynamics, atmospheric chemistry, things like that at the University of Iowa. I got to put a plug in for one of my sponsors, which is a new project that I'm very excited about through the Iowa Space Grant Consortium. We're looking at multi-scale carbon and nitrogen fluxes in the agricultural landscape. This is one of my sampling stations, which is the WB television tower east of Iowa City, where we're sampling CO2 at 1,158 feet above the ground. And then I have a partner from civil environmental engineering who's looking at carbon fluxes at the soil level. So what I'm going to talk about, first I'm going to talk about a natural climate system. I'm going to talk about climate forcings, which are things that mankind has done to potentially change the climate. Talk about the observed climate change that's been seen mostly over the last 150 years. Talk about a little bit about how climate is predicted, and then this concept of avoiding what needs to be done to avoid dangerous climate change. I want to leave a little time left over for a game at the end, which I have prepared for your enjoyment. If I get any hecklers, I'm going to make you play the game immediately. No, please feel free to interrupt me and ask questions during the presentation. I was just reading about communicating science to the public, and one of the time-honored rules is to avoid scientific jargon. So I've tried to do that, tried to avoid terms that are only meaningful to scientists who study this. There are 2 exceptions. One is the word anomaly, which I will use, and I will define it. The other is anthropogenic, which people have decided, a lot of scientists have decided that this is time for this word anthropogenic to leave the world of jargon and just enter the main English language. It's simple what it means. It's anthro-people, genic, genesis, made. So changes to the environment made by people, we call them anthropogenic. And it's a little bit awkward because it comes up over and over and over. We're trying to separate man-made changes from natural system, I mean, that's the whole ball game here. It becomes awkward to keep saying anthropogenic, oh, I mean man-made, so I'm just going to let anthropogenic come out. The natural climate system, we know that it's hot at the equator and colder at the poles, and this is one of the many features of a natural climate system. And this is caused by the tilt of the sun. So these little disks show equal amounts of sunlight. At the equator, that amount of sunlight is concentrated into a smaller area of the Earth. At the poles, it's spread out. So there is less intense solar heating at the poles and more intense solar heating at the equator. So the Earth system responds by distributing or sending heat from the equator towards the poles. And that's the biggest job of the climate system, and that's what causes weather. As this energy comes northward, it brings with it water and clouds and spawns storms. And so the basic physics of climate change is that there are things that we can do to change the balance of energy coming in and energy going out. The analogy that people use is a greenhouse, which does the same thing. It tries to prevent energy from going out of a space to make it warmer. So this is a simplified version of the energy balance of the Earth. So here's the surface of the Earth, and here's space, and here's the atmosphere. Our energy comes in from the sun. And one of the concepts is that there are naturally occurring gases and clouds that trap some of that energy and keep it inside the Earth system for longer than it would if we didn't have that atmosphere. And so that's the greenhouse gases. Here, if we increase concentrations of those greenhouse gases, we can trap this more effectively, keep the energy here a bit longer, and raise the temperature of the Earth in the process. The greenhouse gas is a good thing. Without it, if we had no atmosphere, the Earth's temperature, I forget the exact number, it would be something like 20 below. And the atmosphere that developed on the Earth doesn't have a stable temperature, but a near stable temperature through the presence of greenhouse gases. When you look at time spans 1,000 years, 10,000 years, there's a stable climate. But it's not completely stable. There's things that force it to change its temperature. The biggest forcing is the orbital forcing, so changes in the Earth's orbit. So either the change in the eccentricity, so it's not a perfect circle, the orbit. Sometimes it can stretch out. So that's one change. The Earth can wobble on its rotational axis. We can change its the angle of its axis. Those happen slowly and regularly, and they're called the Milankovitch Cycles. And they cause an approximate 9-degree temperature swing in the mean global temperature, but over very long time scales. So this is 800,000 years. This would be 100,000 years. This right here would be 1,000 years. Another natural forcing is variability in the intensity of the sun. So if the sun gets brighter, the Earth warms up. This is showing solar intensity varying over 150 years. She said, oh, it looks like it doubled, but then you've got to look at my axis here. I start at 1,364 watts, and it caps out at 1,367. So if this was my stock market Dow Jones, it's not changing much. It's staying between 1364 and 1366 for 150 years. You see there's a periodic motion here. It's going up and down regularly every 11 years. That's the sunspot cycle. So sunspots and the sun get more intense. And I actually forget, there's probably somebody in the audience who knows if the sun gets brighter when there are sunspots or when they're not. I don't have. The third natural forcing is volcanic dust. So every once in a while, a volcano somewhere on Earth decides to blow its top. And in that process, it puts a lot of sulfur and a lot of particles very high up in the atmosphere. And that will change the regional and global temperature for a couple years. And this is just showing the amount of particles in the air in the upper atmosphere reconstructed from ice cores for 150 years. So those three are natural variability. And we would call those natural forcings. Then we have carbon dioxide, which is an anthropogenic forcing in part. When we burn fuel, fossil fuels, we make a net emission of carbon dioxide. And this is showing that on all three of these inner planets, Venus, Earth, and Mars, if you look at the radiation coming off of those planets from space, you see a decrease right in the range of radiation that CO2 likes to absorb. So that what this means is that all three of these planets have a CO2 greenhouse gas layer. And then the question comes down to, well, if we increase the concentration of CO2, we cloud up this window and make the atmosphere a better absorber of this radiation, how would that change the temperature? There's other greenhouse gases on Earth. Ozone, water vapor, nitrous oxide, there's many of them. And the reason I'm talking about CO2, it's the biggest anthropogenic forcing. Here's proof that it's the biggest. Here's a pie chart showing the big anthropogenic gases that are doing the greenhouse gas forcing. 2/3 of the forcing is due to carbon dioxide, 1/4 due to methane, and 10% from nitrous oxide. So I'm sure people have seen the emissions graph. So this is emissions of carbon since 1750. This is the Industrial Revolution, so we get this increase. And then a lot of population growth on the planet, as well as increasing per capita emissions. So this is the black line is the total increase in carbon emissions per year. And that's still going up. The breakdown here is by what fuel. So this purple line is what's due to coal. The green line is what's due to oil use. And the red line is due to natural gas. So that carbon so gasoline is 70-some% carbon. It goes into our engine. It comes out as CO2. That CO2 is shown here as this anthropogenic emission of CO2. And that enters what's called the carbon cycle. And carbohydrates have a lot of carbon in them. And plant tissues have a lot of carbon in them. The ocean has a lot of carbon in it. And so this